Hello, today we will discuss discrete probability distributions. First we will discuss random variables. There are two types of random variables, discrete and continuous. And then we will discuss the discrete probability distributions, how to calculate expected value and variance of a discrete random variable. And then we have commonly used discrete probability distributions like binomial, Poisson, hypergeometric. We will also discuss these three discrete probability distributions. So first of all, what is a random variable? Random variable is a numerical description of the outcome of an experiment. So your outcomes may not be numeric, but you can assign a random variable that maps the outcomes with randoms. And we have two types of random variables, discrete and continuous. Discrete random variables they either assume a finite number of values or infinite sequence of values. Even if it is infinite, it is countably infinite. It cannot take any value. It is countably infinite sequence of values, so cannot take any value. Continuous random variable may assume any numerical value in an interval or collection of intervals. For example, first look at this one. So if you roll 3 die, then how many outcomes we have? Total 2 times 2 times 2. We have 2 outcomes for each die, coin. So we have each outcomes for each coin, head, tail, so total 8 outcomes. So what are those outcomes? This is a tree diagram. This outcome, head, head, head. Head, head, tail. Head, tail, head. Head, tail, tail. Tail, head, head. Tail, head, tail. Tail, tail, head. Tail, tail, tail. These are the outcomes. We don't have numeric outcomes, but we can assign a random number, say x is a random number. We can assign a random variable x, which is, say, number of heads. Number of heads in 3 tosses. So now each outcome has now number, such as x, head, 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 which is 3. So we can show it like this here. So what is the value of x if we have this outcome, which is 3? We have 3 heads in that outcome. How about this one? The value of x is 2. This one, 2. Here x is 1. Here 2. 1, 1, and 0. So as you see, random variable is a numerical description of the outcome of an experiment. Here random variable x is the number of heads in 3 tosses. Now Now we map the outcomes with numbers. So if you have this outcome, head, 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 the value of x is 3. If it is head, head, tail, value of x is 2. If it is head, tail, head, value of x is 2. Head, tail, tail, value of x is 1. 2, 1, 1, 0. So x can only take 4 values. It is either exactly 0, exactly 1, exactly 2, or exactly 3. It cannot take any other value. It's either exactly 1, exactly 0, it's either exactly 0, exactly 1, exactly 2, or exactly 3. This means x is a discrete random variable. Continuous random variables can take any value, not just the integers. They can take any value. Such as here, GSL appliances, so X is the number of TVs sold at the store in one day. If you have 4 TVs in stock, then X can only take 5 values. It's either exactly 0, exactly 1, exactly 2, exactly 3, or exactly 4, which is discrete. You can count the TVs sold, yet we have finite upper limit on the number that might be sold. This is discrete. How about this one? Number of customers arriving in one day. Here there is no finite upper limit. You can have 0, 1, 2, 3, but there is no finite upper limit. But this is still discrete because it's countably infinite. We can count the number of customers. We can count the customers arriving. There is no finite upper limit, but still discrete. Continuous random variables can take any value. For example, distance from home to store. This is continuous. Or if you measure the outside temperature. For example, the temperature outside is only limited by the precision of the instrument. Your phone may say it is 73 Fahrenheit, but this is only limited by the precision of the instrument you are using. So with a very precise thermometer, you can have a temperature outside with many digits to the right. Such as outside temperature may be 73.276. You can have many digits to the right. It's not exactly 73. You may look at your phone or your car, it may say 73, but it's not exactly 73. With a very precise thermometer, you can have a temperature outside with many digits to the right. Continuous random variables can take any value in an interval or collection of intervals, not just the integers. They can take any value. For example, here, family size, X is the number of dependents reported on tax return, which is discrete. You can have 0 dependent, 1 dependent, 2 dependent. That is discrete. Distance in miles from home to store, that is continuous. It is again depends on how you measure it. You can get many digits to the right with a very precise meter. You can get very digits to the right. Own cat or dog. Own no pet, dogs only, cats only, dogs and cats. Outcomes are not numeric, but now X, we can say X is 1 if own no pet, X is 2 if dogs only. Now this is random variable X maps the outcomes with numbers, which is discrete because X can only take 4 values. Now the random variables are a numerical description of the outcome of an experiment. And the probability distribution for a random variable describes how probabilities are distributed over the values of the random variable. So sum of the probabilities for all values of the random variable must be 1. So this probability distribution shows how to distribute the total probability of 1 among the values of the random variables. And we can describe a discrete probability distribution with a table, graph, or formula. You can use a special mathematical formula to calculate the probabilities for each value of the random variable. Or you can use the rules of assigning probabilities to experimental outcomes to determine probabilities for each value of the random variable. There are some required conditions for a discrete probability function. F of x, which is the probability function, is denoted by f of x. So discrete probability distribution, so f of x directly assigns the probabilities. So then probability cannot be negative, so f of x must be larger than or equal to 0. And sum of the probabilities for all values of the random variable must be 1. So you cannot have negative probability, and sum of the probabilities for all values of the random variable must be 1. There are 3 methods for assigning probabilities to random variable. Classical method. You use the classical method if you have equal or likely outcomes. Subjective method. You may be expert in one area. You may look at the historical data, but combine this, your expertise, use some data, but not just data. You combine the data with your expertise and assign the probabilities. Or you can use relative frequency method. For example, here, GSL appliances, 0 units sold, 80 out of 200 days, they couldn't sell any television. 50 out of 200 days, 1 TV sold. 40 out of 200 days, 2 televisions sold. 10 out of 203, 20 out of 204. Now we can use the relative frequency method. We calculate the relative frequencies. 80 over 200, 0.4, 50 over 200, 0.25. Now this is the probability. What's the probability of not selling any television? Based on this, it is 4.4. What's the probability of selling 1 TV in any given day? 0.25. What's the probability of selling 2 televisions? What's the probability of selling 3 televisions? What's the probability of selling 4 televisions in any given day? 0.1. You can graphically represent this. This is 1, 2, 3, 4. This is the same information. This is the tabular representation, and this is the graphical representation. In addition to table and graphs, you can use a formula that gives a probability function. If you have a discrete probability distribution, then you can use the formula. Along with tables and graphs, you can also use the formula. And there are several discrete probability distributions specified by the formula, which is discrete uniform. That's the simplest case, is a discrete uniform. Binomial, Poisson, and hypergeometric distributions. So discrete uniform is the simplest case. You have n outcomes, which is the number of values the random variable may assume. Here the assumption is the random variable, the values of the random variable are equally likely. Since total probabilities, sum of the probabilities for all values of the random variable must be 1, if random variable can assume n values, then each value has a probability of 1 over n. For example, if you roll a die, you have 6 outcomes. Either exactly 1, exactly 2, exactly 3, exactly 4, exactly 5, or exactly 6. So what's the probability of each outcome? 1 over 6. Now the expected value, now we will discuss the expected value and the variance of a discrete random variable. So expected value is simply the mean of a random variable, which is the average expected outcome. An expected value of a discrete random variable doesn't have to be the value the discrete random variable can assume. So an expected value does not have to be a value the random variable can assume, which is sum of expected value of x, which is denoted by mu, sum of x times f of x, which is the sum of each random variable value by x multiplied by its own probability f of x. For example, if I roll a die many times and then average my roll, what should I expect the mean to be? Such as I roll it 1, write it down, roll it again, write it down, roll it again, roll it again, and I do this many times, say 1,000 times, and then average my outcomes. Average all the rolls, say I do this 1,000 times, and average the rolls. Then what should I expect that mean to be? If you think the common sense wise, it is you have total 6 outcomes. They're all equally like the outcomes. So then that mean is 3.5. So where the 6 outcomes and each number is equally likely to occur, so the mean is 3.5. This is what the expected value is. So then f of x, so you have 1, 2, 3, 4, each has 1 over 6. X times f of x, so 1 over 6, 2 times 1 over 6, 2 over 6, 3 times 1 over 6, 4 times 1 over 6, which is, once we add these, this is 21 over 6, so which is equals to 3.5. So expected value is it is like the long run average. You do the experiment over and over again and average the outcome. It is the mean of the random variable, which is the weighted mean. Weights are the probabilities. And variance summarizes the variability in the values of the random variable, which is denoted by sigma square, which is now the sum of the square deviations of the random variable from its mean, which is the weighted average of the square deviations of a random variable from its mean. So this is sum of the square deviations multiplied by So x minus mu squared times f of x. Which probabilities? F of x are the probabilities. Standard deviation is the positive square root of the variance. So variance summarizes the variability in the values. Now for the GSL appliances, how do we get the expected value? We multiply x by f of x, so 0 times 0.40, 1 times 0.25, 0.25, 2 times 0.2, 0.4, 3 times 0.05, 0.15, 4 times 0.1, 0.4. And once you add this, it is 1.2. This is the expected number of TVs sold in a day. For example, if they make $100 profit for each television they sold, then what is their expected daily profit? 1.2 times 100, so $120, their expected daily profit. And we can calculate the variance also. X minus mu, so 1 minus 1.2 3 minus 1.2 and then square those. Negative 1.2 square, 1.44, 0.8 square, 0.64, 1.8 square, 3.24, 7.84. X minus mu square times f of x, so then 1.44 times f of x 0.4, 0.576, 0.04 times f of x 0.25, 0.64 times f of x 0.2, 128, 3.24 times 0.05, 7.84 times 784. And the variance, which is denoted by sigma square, which is sum of x minus mu square times f of x, which is sum of these values, 1.66. So as you see, expected value is 1.2, but x cannot be 1.2. Random variable x is either 0, 1, 2, 3 or 4. But expected value doesn't have to be the value the random variable can take. And variance is 1.66 TV squared. Then the standard deviation is square root of the variance, which is 1.288 TV. discuss the random variables. We have two types of random variables, discrete and continuous. We discussed the discrete probability distribution. Now we will discuss commonly used discrete probability distributions like binomial, Poisson, hypergeometric. Binomial probability distributions, a discrete probability distribution, it has many applications, and it's also associated with the multiple step experiment that we call the binomial experiment. If we know that we have a binomial experiment, we can easily use the binomial probability distribution function to assign the probabilities over the values of the random variable. What are the properties of a binomial experiment? Experiment consists of a sequence of n identical trials. So n is the number of trials. And these are identical trials. We have two outcomes considered as success and failure on each trial. Two outcomes are possible. Success doesn't necessarily mean a good thing. Failure doesn't necessarily mean a bad thing. Success means objects or individuals that possess the desired or specified property. So two outcomes, success, considered as success and failure on each trial. P is the probability of success. So which is probability of success is denoted by P and doesn't change from trial to trial. And the trials are independent. Probability of success doesn't change from trial to trial, and the trials are independent. And we are interested in number of successes occurring in n trials. So x is the number of successes, random variable x, in the n trial. So n is the number of trials, p is the probability of success on one trial, and p is constant, it doesn't change from trial to trial. For example, you toss the coin 5 times. What's the probability of getting exactly 2 heads? So this means if a coin is head, it is considered success. If it is tail, it is considered failure. Is this a binomial trial? Do we have n identical trials? Yes, we have 5 tosses, identical trials. X is the number of successes occurring in the n trials, so the value of x, we need x equals 2. Do we have 2 outcomes considered as success and failure? Yes. If it is head, it is considered success. If it is tail, considered failure. What is the probability of success on one trial? 0.5. And it is constant. It doesn't change from trial to trial. So, if we count the number of heads appearing over the 5 tosses, this has the properties of a binomial experiment. So the experiment consists of 5 identical trials. Each trial involves the tossing of 1 coin. And 2 outcomes are possible for each trial, a head or a tail. Probability of head and the probability of tail are the same for each trial. And the trials are independent because the outcome on any one trial is not affected by what happens on other trials or tosses. So the properties of the binomial experiment are satisfied. Once we know we have a binomial experiment, we can easily use the binomial probability function to calculate the probabilities. Here x is the number of successes, n is the number of trials, p is the probability of success on one trial, n is the number of trials. And f of x is the probability of x successes and trials. So this part, which is the combination n choose x, which is n factorial over x factorial times n minus x factorial. This part gives the number of experimental outcomes, providing exactly x successes in n trials. And this part gives the probability of a particular sequence of trial outcomes with x successes in n trials. Let's look at this example. Evans Electronics is concerned about a low retention rate for its employees. In recent years, management has seen a turnover of 10% of the hourly employees annually. So for an hourly employee chosen at random, management estimates a probability of 0.1 that the person will not be with the company next year. Choosing 3 hourly employees at random, what's the probability that one of them will leave the company this year? Now let's look, is this a binomial experiment? Do we have n identical trials? So we have n is 3 here, we choose 3 hourly employees. And so yes, we have n trials. Do we have 2 outcomes for each trial? Yes, either employee leaves or stays. And here, since we are counting the number of the employees who leave the company, the leaving the company is considered success. Success doesn't necessarily mean a good thing. So then we have 2 outcomes, leave, stay. We are interested in the ones that leave the company. So then if an employee leaves, that is considered success. What's the probability of success then? Which is 0.1. That's the probability that a person will not be with the company next year. And we assume that the trials are independent, so they don't affect each other. One person leaving the company doesn't affect the other person leaving or staying. So such as, this is first employee leaves, other stays. What's the probability of this outcome? Or we can say leave, stay, stay. Probability that employee leaves the company is 0.1. So then what's the probability that employee stays? 0.9. Since we assume they are independent, we can multiply these, because remember, if A and B are independent, what's the probability of A intersect B? Probability of A times probability of B. If A and B are independent. This is only true if they are independent. So if we assume that they are independent, so now we can multiply this to find this probability. So what's the probability that first employee leaves, other 2 stays? 0.1 times 0.9 times 0.9, which is 0.081. This is the probability of this sequence. How many other sequences do we have that ends up with only one employee leaves the company? So then you have stay, leave, leave. Stays with probability 0.9, leaves with 0.1, leaves with stay, leave, stay. The one ends up with one leave the company, the other two stays. Same probability 8-1. What is the other sequence? Leave, stay, no, we did that one, so stay, stay, leave. First one stays, second one stays, third one leaves. Probability 0.081. So then these are just in the sequences that ends up with one, only one leaves the company. Such as you have employee A, B, C. A leaves, B, C stays. Or B leaves, A and C stays. Or C leaves, A and B stays. So we have three outcomes that ends up with one leaves the company, other two stays. So what's the probability that one of them will leave the company, which is sum of these probabilities, which is 0.243. And we can calculate also other probabilities. Like here we don't use the binomial function, but we can use the function. This is n is 3 factorial, p is 0.1, 0.9 to the n minus x, which is 2, 0.243. So if we know that we have a binomial experiment, we don't have to list all the outcomes, calculate the probabilities of each outcome. We can directly use the binomial function to find the probabilities. This is a tree diagram for this example, such as employee A, B, C. A leaves with probability 0.1, stays with probability 0.9. Same thing, leaves with probability 0.1, stays with probability 0.9. So how many total outcomes we have? 8. Such as this is leave, leave, leave. Leave, leave, stay. Leave, stay, leave. Leave, stay, stay. Stay, leave, leave. Stay, leave, stay. Stay, stay, leave. Stay, stay, stay. These are the outcomes. So if this happens, then x is 3, because 3 leaves the company. We are counting the number of employees that leave the company. And if this happens, x is 2, leave, stay, leave, 2 employees leave, so the value of x is 2. Here value of x is 1, here 2, 1, 1, 0. And we can calculate the probabilities of each outcome, such as this one. They leave 0.1, 0.1, 0.1, which is 0.001. Leave with probability 0.1, stay with probability 0.9, 0.009. And these are the same. And the stay, so employee A stays with probability 9, 0.9 times 0.9 times 0.9, 0.729. There are some tables, binomial table that you can use at the back of the book. table 5, such as here n is 3, x is 1, these are points. P.1, so n is 3, x is 1, P.1, 0.243, x is 0, P.1, 0.729. We can use the tables also. And the expected value of a binomial distribution is, so remember the expected value is sum of x times f of x, such as in our case x can be 0, 1, 2, 3. And what's the probability? X is 0, 0.729. X is 1, 0.001. So we can calculate the f of x which is x times f of x, so 0, 0.243 and 0.0030. So the sum is 0.3. But if we know we have a binomial random variable, we don't have to list the outcomes, probabilities, and calculate it like this. We can easily calculate the expected value, which is n times p. If we have a binomial random variable, here n is 3, p is 0.1, so which is 0.3. And the variance is n times p times 1 minus p. This is only true if you have a binomial random variable. These are the expected value and variance of the binomial distribution. So we provided formulas for computing the expected value and variance of a discrete random variable. In a special case where the random variable has a binomial distribution with a known number of trials and known probability of success, the general formulas can be simplified. But this is only true if you have a binomial random variable with known number of trials and known probability of success. Now we will discuss Poisson probability distribution. This is also a discrete probability distribution like the binomial. So binomial distribution, x is the number of successes. So what are the values x can take? You can have 0 success, 1, 2, depending on n, whatever that n is. You cannot have, such as if n is 3, you cannot have 4 success out of 3 trials. Like in this case, what are the values x can take? X is either exactly 0, 1, 2 or 3. Can go all the way to n. For the Poisson distribution, Poisson random variable is useful estimating the number of occurrences over a specified interval of time or space. So you are counting the number of events. It can be number of failures, number of customer arrivals, number of patient arrivals. So there is no finite upper limit. So x can be 0, 1, 2. There is no finite upper limit, but it is countably infinite. For example, if this is number of customers arriving, you can have 0 customer, 1 customer, 2 customer. You cannot have 1.2 customer or 3.56 customer. This is countably infinite. There is no finite upper limit. Still discrete. For example, number of vehicles arriving at a toll booth in 1 hour. You have specified interval of time or space, and you are counting the number of occurrences. So the properties of the Poisson experiment, the probability of an occurrence is the same for any 2 intervals of equal length. And the occurrence or non-occurrence in any interval is independent of the occurrence and non-occurrence in any other interval. And this is the Poisson probability function. X is the number of occurrences in an interval. Mu is the expected number of occurrences in an interval. E is a mathematical constant, approximately 2.71828. The E here. (2.71828). F of x is the probability of x occurrences in an interval. So there is no stated upper limit for the number of occurrences, but in practical applications, x will eventually become large enough so that f of x is approximately 0, because you are dividing this to x factorial. For large values of x, you are dividing it to a very large number, because this is x factorial. So f of x will be really small for practical applications. So it will be approximately 0, even though there is no finite upper limit. In practical applications, x will eventually become large enough so that f of x is approximately 0 and becomes negligible. This is a typical Poisson problem. Patients arrive at the emergency room of Mercy Hospital at the average rate of, so mu, 6 per hour. What's the probability of 4 arrivals in 30 minutes on a weekend evening? If you have on average 6 patients per hour, then how many do you have per half an hour? Which is 3 per 30 minutes. Now f of x is mu to the x. So now we are calculating the 30 minutes, so then mu is 3. So then probability x equals 4. What's the probability of 4 arrivals in 30 minutes? Mu is 3. So 3 to the 4 times 3. 0.168. So if you don't know how to put the E in the calculator, you can type it like this, because E is approximately 2.71828. And here we see the Mercy Hospital number of arrivals in 30 minutes. You can calculate all these probabilities. As you see, there's no finite upper limit, so X can be, in this case, 0. You may have 0, 1, 2, 3 patients, no finite upper limit. But even for 10, we have very small probability, so it's almost 0. And the property of the Poisson distribution is the mean and variance are equal. So in this case, mean is 3 for during 30-minute period, so the variance is also 3. Now hypergeometric is another discrete probability distribution. It is closely related to binomial distribution, but the difference is the trials here now are not independent, and probability of success changes from trial to trial. Assume I have an urn here, say 5 red balls, 3 black balls. I select 2 of them without replacement. What's the probability of selecting red ball, which is 5/8? We have total 8. But depending on whether this one is red or black, so if this is the red, now what's the probability of selecting another red ball? Now we have 4 red one left out of 7. If the first one is black, then what's the probability of selecting the red ball on the second time? Then it will be 5/7. So now probability of success changes. So you select the red one is 5/8 probability of selecting the red ball. But now depending on whether this one is red or black, the second one, now you have 7 left. So if this is red, selecting another red ball will be 4/7. So probability of success changes. This is the hypergeometric probability function. Now we have total n number of elements in the population. N is the number of trials. This gives the number of ways you select n objects out of n, or n individuals out of n individuals. R is the number of elements in the population labeled as success. X is the number of successes. If in the population, so you have total n. If R successes we have, then this means another n minus R must be failures. Failure doesn't necessarily mean a good thing, or success doesn't necessarily mean a good thing. Failure doesn't necessarily mean a bad thing. And in this sample, if we have x successes, then the other n minus x must be failures. So this gives the number of ways selecting x successes out of R successes. Then you have n minus x failures left out of n minus R failures. So you select n minus x failures out of n minus R failures. So this is a number of ways x successes can be selected from a total of R successes in the population. Now in the population, if we have R successes, the other n minus R are the failures. So in the sample, if we have X successes, the other n minus X are the failures. So this gives the number of ways n minus X failures can be selected from a total of n minus R failures in the population. And this is the total number of ways, then n elements can be selected from a population of size n. Let's look at this example. Bob Never Ready has removed 2 dead batteries from a flashlight and inadvertently mingled them with the 2 good batteries. Now 4 batteries look identical. So total 4. Bob now randomly selects the 2 of the 4 batteries. What's the probability he selected 2 good ones? So then 4, 2 good, 2 bad. And we select 2 of them from 4. We want all good ones. We don't want bad ones. 0 bad, 2 good. So now this gives the total number of ways selecting 2 batteries out of 4. And now we have total 2 good batteries and we want 2 of them. This gives the number of ways selecting 2 good batteries out of 2 good batteries. Now how many bad batteries we have? 2. Do we want any bad? No. 2 choose 0. These are the combinations. So then this is 2 factorial. Two choose 0 is 1. 0 factorial is 1. This is 1 over 6. 2 and CR2. This is 1. So we can do it 2 times. This is 1, 2. 2 choose 0 is 1. Divided by 4 choose 2. 0.116, which is 1 over 6. From 1667. This is the mean and variance of the hypergeometric probability distribution. So we discussed the random variables, discrete and continuous random variables, how to calculate the expected value and variance of a discrete random variable, discrete probability distribution, and we will discuss some commonly used discrete probability distributions like binomial, Poisson, and hypergeometric.